I'm Dave Evans, and I'm going to briefly describe our work on activation compression, JPEG-ACT. First, I'm going to talk about neural network training performance. I've plotted a series of networks with accuracy on the y-axis and total computation to train on the x-axis, measured in number of days to train at 1 petaflop per second. There's a clear trend. As accuracy increases, so does the amount of computation required to train. This is why we look to accelerate training as opposed to inference. Activations are a form of intermediate storage used when training neural networks. On the right graph, I have a timeline from 2013. The blue line shows how activation storage requirements have continually grown over the past 2 years and approached hundreds of gigabytes. The red line shows how memory size for graphics processors, or GPUs, has not increased at nearly the same rate. Older networks, such as VGG, had a very small activation footprint and easily fit onto a single GPU. This gap is due to physical limitations, such as bandwidth and memory technology, and is unlikely to improve as accelerators are increasing on-chip compute densities. In JPEG-ACT, we address the problem of memory during training through the insight that convolutional neural network activations look like images. We can use similar techniques to deal with both of them. We reduce memory consumption by offloading activations using a compressed offload. This has the advantage that we require no changes to the network training procedure and no changes to the network. We use an optimized compression method that involves lossy compression. I have a summary of our results on the right, where better are to the top right. Compressing the activations using JPEG leads to higher performance but a low accuracy. The JPEG parameters are optimized for image compression, so when we optimize them for CNNs, we significantly improve accuracy. JPEG-ACT accelerates offloads by adding a compression-decompression unit, or CDU, which is connected to the GPU. When training neural networks, activations are generated in the forward pass. After the forward pass is completed, activations are consumed in the backward pass of training. For VDNN, a prior work, activations are offloaded to the CPU memory over PCI Express. During the backward pass, each activation is brought back from the CPU memory and placed in the GPU memory before use. We use a compressed offload, which adds a CDU, custom hardware to compress and decompress the PCIe interconnect. This compression-decompression unit, although it adds hardware to the GPU memory system and DMA, has many advantages, such as operating in parallel with the forward and backward pass to avoid extra computational overhead, and allowing a significantly higher offload rate than the PCI Express only solution. In our paper, we derive a technique for optimizing the lossy compression method. We do this process offline, and to clarify, we're optimizing the compression, not the neural network weights. We use simulated compression and error metrics to tune the JPEG parameters for CNN error sensitivity. This results in a 50% increase in compression ratio and halves the change in accuracy from an uncompressed network. The second major contribution is optimizing the JPEG compression algorithm for CNNs. The improvements are switching from division to shift quantization for area reduction, and switching from run length encoding to zero-value compression for better zero extraction. These contribute to better compression, leading to significant performance increases over prior works. Thanks for listening.